got it. Yeah, all right. Yeah, now I know what you mean. Okay. Okay, let's see. So the thing that I would like to do to start is my first lecture today is in many ways going to be an overview and a setup for my own subsequent lectures, which I have in mind, plus Frank's lectures, which are happening. Did I not do something? Is that okay? Maybe we should wait for the technical. Are we okay? Okay, good. So what I'm going to do is give kind of an overview, which we'll set up for my own lectures for the rest of this week. We'll also set up for Frank's lectures, and also Steve Audi. I haven't seen him here, so he'll be. These lectures this will all be kind of a really fast. This part of it will be a very fast overview of what's going to come later, and will also put me in a position to talk about a critical issue that will inform our discussion of dependent types. So that's my major theme for the week, is talking about dependent types, which perhaps some of you are interested in. But I can't assume that you all have, I don't think I should assume that you all have the background that you need in order to appreciate what's going on with the theory of dependent types. So what I want to do is I want to start out with just a bit of a crash course sort of overview of a topic called Intuitionistic Logic, which I'm going to broach from simultaneously from an algebraic and a proof theoretic perspective. Okay, so that's what's going to happen. So the way I like to describe this is I think of intuitionistic logic. Maybe you have or haven't heard that term before, but the way I like to half jokingly, but only half, think of it is it's logic as if people mattered. Okay, this is my view about what intuitionistic logic is all about. And the reason it's all about that, and why I present it that way, as if people matter, is because it is very much focused on the idea of the process of doing math and eventually doing computer science is a process of communication. It's all about communication of knowledge. Okay, this is what we want, is communication of knowledge. This is the basic idea. And so what I mean by this is we have the primitive notion in logic. The main thing we're interested in is expressing whether A is a proposition, and Frank is going to go into a lot of this in great detail, which says that A is sort of a sensible assertion. Let me just write A sensible here on the writing, but A is a sensible assertion. It makes sense to write this down. And then the crucial thing is A is true, which is the kind of thing that you learn in school. So an assertion is true, and what it means is that, and this is the important part where people come into it, it means I know a proof of A. So the idea is that this is just syntax for what in a textbook you write theorem, there are infinitely many primes. Infinitely many primes, for example. What you are saying is, we'll call this A. Okay, let's give that a name A just to line up the notation. And when I say theorem A, it means I claim that A is true, of course, that's what it means. But if you're doing a math book, you don't get to just sort of, or in your homework or something, you don't just get to assert that something is true, or you do, but it takes a certain amount of credibility to get away with that. Because implicitly, all right, is the idea that you know a proof of it. And so invariably what comes after here, after you state theorem, is there's a proof, and there's some sort of an argument, and some sort of end of proof marker, okay, that goes on here. So that's the notion of truth. So the idea here is that something gets to be true only by virtue of your having a proof. That is the critical idea. So this is a little bit different from like what you probably learned in school a long time ago. I'm sort of guessing because it's fairly standard. Probably somewhere along the way, people taught you about truth tables. At least my experience was when I was like a young teenager. In geometry class, we spent some time learning the truth tables for all the logical connectives, and you go through all these things. And then seemingly they completely change the subject and start doing Euclidean geometry, where the idea, the emphasis is on writing a proof, and you have this sort of chart form where you would write down a deduction. And in some way, it's not really very strongly connected up. What does this story about truth tables and booleans and bits have to do with the writing of the proof, and what is the grammar of proof? And that is a central idea. So proof theory, in some way, which we're going to talk about here, Frank is going to talk about a lot, okay? Proof theory is really talking about a formal or precise grammar of proof, you might say that. Okay? That is a notation system, if you want to say it. You can think of it as a notation system, a notation for proofs. Okay? And moreover, it's going to involve a notion of equivalence or execution of proofs, equality of proofs. And in fact, this idea of equality of proofs is where I'm going to try to get to in this lecture, is it gives you a notion of when are two proofs the same. Before I get to that, and that will motivate something else, let me just mention something about grammar of proof. Probably many of you, a lot of you here, maybe, it's possible that for this audience this isn't the best example, but for many people at some stage in their career have a lot of trouble understanding what is a valid proof. Okay? I know from teaching at university for quite a long time that many students have a hard time getting it. So one way to address the problem, there are many ways to address the problem, is to think of it like a kind of English composition class, and sort of proof theory is kind of the math composition class, where the idea is to, let's get the mechanics down of exactly what it is to constitute a proof. Okay? That's what's going to happen. So the idea about proof theory is to do that, to give us a formal notation for proofs. And then it will raise, and I'm going to get to this, back to this by the end of my lecture, an important issue of equality of proofs, which leads to the idea directly to the idea of an algebra of proofs. Because remember that which is this algebraic view that I was alluding to before. Because remember, in algebra, the basic idea of in algebra is you're calculating whether one expression is equal to another, maybe. So when you learn, elementary algebra in school, you learn to manipulate polynomials, for example. So you have various forms of expression, and you want to know when are they equal. Or if you look at more abstract algebraic structures, groups or something, they're given by equational laws. So you're worried about equality. Okay, you're always dealing with equality. So what is going to happen is I'll motivate this a little bit. So proof theory will give us a notation, and the algebra will give us some way of reasoning about when are two proofs equal. So the reason to do that is to give us a concept of what abstract object are we talking about. You see, because if you give some idea of just a notation for proofs, that's well and good, but then you'll find, as we'll see shortly, there are little variations you can put into a proof, and you wonder, well, which ones matter and which ones don't. And you sort of would like to quotient out by some equivalence relations, and I'll talk about various degrees of doing that, about the equivalence relation, in order to isolate the abstract character of the proofs as some kind of mathematical objects. So what we wind up with at this point, which is very important to intuitionistic logic, is the idea that proofs are mathematical objects. Okay, I have to say mathematical object. I'm trying to be very emphatic here in the way I explain things. Because in the conventional story that people tell you, like the one I learned that I explained to you when I learned geometry a long time ago, you have these, Booleans. The mathematical objects in play are the Booleans and the Euclidean plane and various geometric figures. Those are the objects you play with. The proofs are just the way you talk about them. Okay? And you learn how to write those things down and how to write a convincing argument that shows that two triangles are congruent or so on and so forth. Well, that's fine as far as it goes. But the interesting thing here when you engage in proof theory and develop the algebra of proofs is that the proofs themselves become mathematical objects. Okay? They are things that have exactly the same status as every other mathematical object, as points in the plane, as functions in space, as geometric figures, as. all the proofs become mathematical objects. Now, this is not to say, for those of you, obviously you're all computer science people or have some experience in computer science, this is not to say the trivial thing that things can be quoted and used as strings because of the equivalence relation. Okay? So the idea is their proofs are mathematical objects, and I would even emphasize at the risk of being overly underlining the same point, I'll double emphasize this point. They're abstract mathematical objects, by which I mean they're characterized by an algebra. They have some kind of notion of equivalence between them, and they thereby, and then the interesting point will be that equal proofs have to be interchangeable in all contexts. So then it's a much more subtle business than just talking about something like strings. So I don't want you to get off, run off and say, oh yeah, I know all about quoting and string, because it's pretty much irrelevant. Okay? And we'll come back to that in a moment. I mean, you can do that, and I'm not disputing that, but that's not the interesting thing. That's not where the action is. Okay, so we're going to see this. So the idea of intuitionistic logic is you take the idea of a proof very, very, very seriously, much more so than any other branch of logic. And there's a payoff to this, and there are many payoffs to this, and boy, we'll spend the whole couple of weeks here drawing out the implications of this fact. But the one that I can say straight away that comes out of this is if you think about what you learned in algebra, when you learn in algebra, one of the things you get, and in fact the origin of the word, something wrong? Oh, did somebody say no? Okay, the origin of the word algebra comes from an Arabic word meaning, someone here who speaks Arabic will check me, a method of calculation. Okay, that's where it comes from. It's Al-Khwarizmi's work from, I think, like the 13th century. So it means a method of calculation. Okay, that's the idea. So originally, like most branches of math, these methods were invented basically in order to figure out ways to make money. Okay, this is the way probability was done. This was invented for this reason. Algebra was done as ways of doing calculations of measurements and so on. So it's a method of calculation, which in this case we will think of as computation. Okay, so that's an important point, is that by thinking of proofs as having an algebraic structure, that algebraic structure gives rise to a notion of calculation. That notion of calculation is a model of computation. Okay? So what we're going to have then is we're going to have a notion where proofs are programs. So this is the idea. So it's method of calculation. Proofs are mathematical projects, and in fact proofs are nothing other than programs, computer programs, things that can be executed or can be calculated with. Okay? So they're programs. They're programs, to use a jargon, to foreshadow a jargon that I'm going to use a little bit later, they're going to be programs, the jargony way of saying it is in extension or viewed extensionally, or that's the jargony way of saying it. I'll explain later what that means, or as abstract objects. So I have to, excuse me if I'm being overly emphatic, but I do have to emphasize it's not an issue about quoting. Don't get that idea, okay? So it's really treating programs as abstract mathematical objects. So that's the basic setup, okay, of what intuitionistic logic is all about, okay? And what Frank is going to be doing is talking a lot seriously about proof theory, and I'm going to give you a little kind of foreshadow of that because I need to set up some things for you. And what Steve Audi is going to be talking about is the algebra of proofs or category theory. And what everybody is talking about is really just computer programming. Okay? So there's this thing which I like to call the sort of Holy Trinity here of computer science. Okay? So we should keep this over the side, which is I like to call the Holy Trinity, which is the correspondences between proof theory, which is sort of the theory of logic and proofs, algebra and category theory. And then the subject in the computer science side is programs or type theory. Those are the same thing. Okay? And these all have tight correspondences. This is like what I tongue-in-cheek call the doctrine of computational Trinitarianism, which is the the computing in three persons principle, that we have that the idea of a computational concept arises as, perhaps it arises as a notion of computing, but it may also arise, the same concept may also arise in algebra, and it may also arise in logic. And in fact, I would turn that the other way around and give it a more normative force and say, you don't know what you're talking about until whatever idea you come up with, till you understand it all three ways, as a notion of computation, as a notion of proof, and as a notion of algebra or algebraic structure. If you find something that has good meaning in all three senses, you have what I would call a proper scientific discovery. Okay? At that point, you've done something which is permanent. You've really made something permanent, something that will last to eternity. You've really discovered something significant. You've got a real discovery if you discover some conception that makes sense from all 3 points of view. So the beauty of this is that the way I like to think about it is it's a way of making working on these problems in a certain way meaningful or worth doing. Personally, your opinion may certainly vary. I find nothing more dreary than trying to chase around the recent trends of some bozo at some company who is telling us that we ought to be doing some object-oriented mumbo-jumbo with something or other. Okay, this is like, I'm not interested in this. Okay, this is like completely unimportant to me. These are the vagaries of technology that come and go, and they're popular because some big company says they're popular, and then they're not because that big company goes out of business or whatever. It's a load of nonsense, right? So if you're interested in science, maybe you're not, but if you're interested in science, this is the scientific framework for talking about programming languages, and this is what we're doing. So the reason I wish to start out by talking about logic is because, well, it's an entry point. And we'll run around this circle between me, Frank, and Steve Audi. We'll run around this circle and show you all the aspects of what we're doing. Okay, so that's the plan. So that's why I think these concepts are very central to the study of programming languages. That is, and this is what I would call the real study of programming languages. Okay, this is the real stuff where we're down to like what are the fundamental principles of computation, and that's the idea of it. Okay, that's what's going on. Okay, so good. So now I want to say a few things about how this is sort of set up in order to get somewhere, to get started, so that I can say something. What I want to end up today is saying something about the notion of equality of proofs. So in order to do this, I need to set up a little bit of machinery. So there's a few things that Frank is going to develop, and I'm going to write it over here as a chart, sort of on the proof theory side. And I need to use this to get going, and I need to do this on the algebra side. And what I'm going to do for the purposes of making my points is I'm going to present a slightly degenerate form of what Steve Audi will be talking about. So I will be looking at a kind of limited formulation of category theory in this setting in the form of preorders. So I'm going to be looking at the structure of certain structured preorders. This is what we're going to get to, and I'll show you what I mean by that in a minute. What Steve will do is to develop this properly into the theory of categories. So the theory of categories one way of seeing it is as a substantially, to say the least, generalization of the idea of a preorder, or the other way around, a preorder is a very substantially degenerate form of category. But I'll leave Steve to talk about that in detail. Okay, so I just want to give you a flavor. So one of the elements of the correspondence is the following one, which is that I want to bring out in this chart, which is the idea of going back to what I said before, this primitive judgment of truth. I would now like to talk about, briefly, I need to talk about it here, the notion of entailment. So I want to think of this as the idea, which is also known as logical consequence. So Frank is going to go into this in great detail, but I need to I'll give you a little foreshadow a little bit what's going on. And the idea is this. We started out with saying, well, we were interested in judging, as the terminology will go, whether a certain proposition is true. But in reality, it's not so often that you just say outright that a certain proposition is true, but rather you say that it's true under hypotheses. So what you do is you have what are variously called hypotheses, or maybe they're called assumptions, okay, or words like that. And this is your conclusion, okay? And that's a typical terminology. And the idea, as you want to say, is that essentially that A is true, given that, and now everything resides in the given that the A1 is true and various other things, AN is true. That's the basic reading of this. And this is, for those of you who are not familiar, that's called a turnstile. And it is what it is. That's what people use it. That notation goes back to Frege in the late 19th century. Okay, so this is the idea. So what we have is this idea of logical entailment. And the interesting thing that I want to point out about the logical entailment, just to draw these correspondences between, and in the middle, what I'm going to end up writing here are types. So let's put it in the middle. But in the starting point, what I'm going to do is go on the ends, and then we'll make it meet in the middle. That's my plan. Okay? So I'll just give you a flavor. Okay? So here's a flavor. So the flavor is, if you look at this structure, I want to point out a couple of things about this notion of entailment. I am hand-waving a little bit. Okay? But the reason is I'm doing an iterative deepening. So this is supposed to be like high-level intro. So all the details will emerge, but let me hand-wave a bit. Okay, so hand-waving a little bit. Given the reading that I mentioned to you before, you would expect that if you assume something is true, then it's true, okay, which is the principle of reflexivity. Okay, this is the hand-wavy part, okay? So I'm hand-waving. That ought to be part of the meaning of entailment. From a sort of algebraic or order theoretic point of view, that can be read as saying A is less than or equal to A. Okay, so it's an order. In other words, we can read this thing as being a kind of less than relation, and in fact what we're going to read it as is a kind of mapping relation is what's going to happen later. So on the category theoretic side, I said I wasn't going to do this, but I'll fill it in a little bit. You have a map. For any object A, you have the identity map from A to itself. That's eventually what's going to happen. It doesn't fit on my board. From a pre-order point of view, it just says A is less than or equal to A. Another interesting fact that you get, so this might be called reflexivity. Another interesting fact is transitivity, or the Lemma Rule. And this tells you, there are various ways to write this down, but again, like I say, I'm giving a little overview. If B is true on the basis of A, and A is true on the basis of C, then we can conclude, and that's the way in which we write it, that, what did I do here? That B, boy, I screwed my letters up. That B is true on the basis of C, if I did that right. Okay, and if I chose my letters better, it would have looked nicer. Okay, so that's a principle, and we can read this as a principle of transitivity, right? Because what is it saying? It's saying if A is less than or equal to B, and B is less than or equal to C, so did I mess it up? Then A is less than or equal to C. What did I do wrong here? Let's do it to make it look better, okay? So I want A less than B, B less than C. Let's do it like that. I got my letters wrong. And then it will be A less than C. That way it'll work. Okay, good. So then the notation will work. Then A is less than or equal to C. And this is just the idea, if you look in a category, if you have a map from A to B, and if you have a map from B to C, then you can compose them, right? You can do G after F and get a map from A to C. That's what will be coming up in categories, okay? But here it's the principle of transitivity, okay? So already we can see some sort of familiar looking structure, okay, is emerging, all right? That's the idea. So what you see on the proof theory side, so what does this correspond to? If you think of this in terms of logical reasoning, okay, if you think of this as logical reasoning, then it corresponds to what I would call the Lemma Rule, right? It sort of says, I want to prove C. You're always working on the basis of some assumptions, All right, degenerately, we'll get to the degenerate cases in a little later, but let's say we're always working under assumptions, but we're trying to show C. Then what you can do is you can break it down and say, well, B is sufficient for C, and you give an argument, and then you separately prove B. Okay? So that's the lemma rule. That's what's going on here. Okay, so this is the idea of a lemma, appealing to a lemma. Okay? And so that logical principle is really can be cast algebraically as the transitivity of this preorder. Okay, so those are two examples. There are other examples I can give. Let me just check my notation. Okay, which, yes, I will do that. Give me a second here. I have to think about how I want to do that. Okay, I'll get to that in a second. All right, any questions so far? Okay. No? Any questions? No, you're all with me? You've all seen all of this before? I don't know any of you, except possibly one or two of you. It's all completely familiar? Okay, maybe, maybe not. All right, well, please interrupt me and ask questions as they arise. It's more fun for everyone if you jump in. Okay, so what I want to do now is, so that's the beginnings of the structure. So now I want to look at fleshing out this structure a little bit. And so let me do it by starting, I'm going to need this to remain visible. So let me throw it up there, and then I'll come back to it in a minute. Okay, so let me observe something for you. Again, I'm at the level of, very high level thing here, of just trying to give you some main ideas. Okay, so here's this like kind of hand wavy thing. So let's look now for a moment, let's switch over. What I want to do is I want to show the interplay of ideas. So let's start on the algebra side here, what I have over here for the preorder structure. So some of you may have come across the idea of a meet, okay, a meet operation, or you could call this greatest lower bound if you want. But let's just look at what that is. So first of all, in a preorder. So I say a preorder is a reflexive and transitive binary relation. So that's what we've got so far. And I want to say that a preorder has meets, okay, means if you give me two elements, they have a greatest lower bound. That's the usual definition of a meet. You can do this also with join, and I'll do that in a moment. Okay. So what is the idea of a meet? Well, the idea is that we have this binary operation that, given two elements of the order A and B, forms another element, which is written A wedge B, okay, which has the characteristic that it's a lower bound for A. It's a lower bound for B. And moreover, it's the greatest such thing. And what does that mean? That says if you have any other lower bound for A and B, then I want to know that the meet is at least that large. And it's written like that. So this is so these are the conditions of what it means to be a meet. Okay, this is the definition of a meet. So if we have binary meets, and then we can also have a trivial nullary meet. Okay, and we can let's see if how do I wish to explain that? So the nullary meet takes no things and forms an object, which is the greatest lower bound of nothing. So the nullary meet means that for any C, C is less than or equal to T, which is, it's usually called T or top, which is the top element of the lattice. So this is the nullary meet. This is the 0 case, right? And this is the 2 case, so this is the binary meet. Okay? And the reason I bring that up is because if you have binary and nullary meets, all binary meets and nullary meets, then you have all finite meets. Okay, that's the idea. Any finite subset has a greatest lower bound. That's the idea. Okay, so now here's an interesting thing about this structure. So that structure would be called a lower semilattice. Okay, that would be the jargon, okay, for such a thing, because it has meets. If you do it around the other way, where you have joins, I'll come back to that later, you can dualize these things, then you get an upper semilattice. So this is called the lower semilattice. So what I want to do now is jump back over on the proof theory side and tell you, well, what did I say when what did I mean? Like, what does that correspond to over on the proof theory side? Well, I claim what it corresponds to is the idea of conjunction of propositions. And here is the idea. Let's think about what the first thing is saying. It's saying that if A and B is true, then surely A is true. That's what it means to be a conjunction. And if A and B is true, that's our entailment, then surely B is true. And finally, and this is the important thing, if we can look at it like this, if C true entails that A is true, so A follows from C, and B also follows from C, you get two results from the same lemma, then you can get their conjunction from that same lemma. That's just transposing from this order theoretic side over into the logic side. All I did is rewrite it, okay? And this is what I have said, okay? So this is what I've done here, okay? So that's an example. Now another thing that is useful, so you can see now that there's obviously some beginnings of a correspondence between the idea of meets and conjunction. So order theoretic ideas like greatest lower bounds transpose over to sort of logical connectives like conjunction in a logical setting. And I wanted to draw a picture somewhere. See if I can find this. There's a useful picture I can draw. I would like to leave this up here. Okay, so let's write it like that, okay? Which is the idea of a Hasse diagram. You're probably familiar with this idea. So the characteristic diagram we have is this. That says I have to think of which direction I want to draw. Okay, so if I take A and B, what we will say is A and B is less than A. You can draw it like that. A and B is less than B. So this is our less than or equal to. That's what I mean by less than or equal to. And if C, okay, is less than or equal to A, and C is less than or equal to B, then C is less than or equal to the meet, A wedge B. So this picture here that I've drawn, okay, corresponds to these three statements that I've written here. And that's an instance, if we were restricting to preorders, that's an instance of what is known as a product diagram in category theory. And Steve will go into this in a lot more detail. But so everywhere you see an arrow, you're supposed to think less than or equal to. The arrow just means it exists or it doesn't. Either it's less than or equal to or it's not, and we have this diagram. And the point is that the solid arrows are sort of universally quantified for any two less than relations like this. There exists, that's the dashed arrow, a relation like this. That's what is being said here. Okay? So this in some way corresponds to that. Okay? So that's a good picture to keep in mind, and you'll use that picture a lot. Okay, so now in order to set up for talking about dependent types, I first need to talk about types. So what I want to do, so now I've started to give you a little bit of a flavor. A lot of this will get developed in much more detail shortly. But what I want to do is I want to go back and now show a correspondence between these ideas and programming languages. Okay. And the idea is the following one. What I want to do is, instead of talking about, so this is a notion of entailment, or we could say, let me figure out where to write. These don't slide, that's a little inconvenient. Okay, so I have to make room. Okay, so what was I going to say? I lost my thread. Oh, yes, right. So the idea was, we said A true is A has a proof. I know a proof. Okay, has a proof or is provable. There's a little worry here. Okay, Frank will make this very clear to you as he goes along, but there's a gross abuses of the word provable, okay, in computer science and branches of logic that confuse matters a lot. Okay? So here I just mean have mathematical proof, by which what am I driving at? I do not mean has a proof in some predefined fixed sense of the word. It just means I know a proof, it's a cogent argument that any of us can understand. This is the human aspect of intuitionistic logic. It's a principle of communication, and whether something is a valid or legitimate communication, whether it works, whether I succeed in teaching you something, is a social construct. It's not defined by fixed rules. There are things that are known to work, but who knows what invention might come up. Okay, so this is what's important here. Be careful about these words. Unfortunately, then you get into crazy, inane discussions that are based on, misunderstanding the meaning of the word provable. So I know it might be a little hard to grasp at this stage of the game, but as things develop, we'll revisit the issue, and I hope Frank will amplify my point. I'm sure he knows very well what I mean. And so, but the thing I want to get at is it has existential force, meaning that it's all about there exists something. I have a proof, there exists a proof, it is provable, right? It's the able, okay? So there's some kind of existential force in this. So what I want to do is I want to just change this a little bit and talk about what it means to actually be a proof, and it's written like this, and this is where we get the correspondence to type theory. So the idea is we'll say M is a proof of A. Okay, that is the idea. So I'm going to have a notation for proof. So this is now where we get to what I was saying to you before about having a notation for proofs. That the proofs become now very, there's a sort of, I'm leading you down this path, and by the time I'm through with you, the world will look rather different to you than it might have done before. And if that's true, that's good. That's the whole point. So, so what I'm